Plenty of you who are here this morning. Good to see you. So Green's theorem. We've been doing Green's theorem in the one direction where we're given a line integral and we turn it into a double integral. But today we're going to look at the other direction. We start with the double integral and we turn it into a line integral. And the typical occasion here where this is useful, if you could please keep quiet. When there's only about 20 of you, I can see exactly who's talking. When there's 160 of you, it's harder to tell. So encourage your friends to come to class, then you can get away with mischief. The typical example here is of an area where you want to work out the area which is framed as a double integral, and then you actually turn it into a line integral around the boundary of the region whose area you want to work out. So, sometimes the double integral, because usually the double integral is easier than the associated line integral, but it can be the other way around. Sometimes the double integral can be trickier than the associated line integral, in which case we can use Green's theorem in the other direction for what we were using yesterday. Please keep quiet. The typical example, although obviously other situations could apply, but the typical example of this is in working out the area of a region where our formula is area equals double integral 1 dA. So our integrand is 1. In order for Green's theorem to apply, we want our integrand to be dq by dx minus dp by dy. So that must mean we require 1 to equal dp by dx minus dq by dy. Other way around, sorry, dq by dx minus dp by dy. Sorry, I'm getting my q's and p's mixed up. If we regard the integrand of 1 to be dq by dx minus dp by dy, and we design, it's up to us, we have the power to design what P and Q are, and we design P and Q however we want to. We can use Green's theorem. And we can turn that double integral into a line integral. So here are some examples. Okay. There you go. No, it's actually getting quite uncomfortably hot in here. So while people are copying that down, let me pause the recording. So here are some examples of what I mean by designing P and Q. For instance, what if Q equals X and P equals 0? Then dq by dx minus dp by dy will be 1. Or what if P is minus y and Q is 0? Then once again, dq by dx minus dp by dy will be 1. Or, and this one's the most popular, I think because it kind of spreads the burden equally across P and Q, P equals minus a half y and Q equals a half x. Because then you'll end up with a half plus a half. So you'll get 1. Obviously, there are infinitely many other options. Because all you require is that dq by dx minus dp by dy equals 1, and I'm sure if you get creative, you can think of all sorts of things. Gosh, you could probably even think of something with coses and sines in it, really. Seeing as we know that cos squared plus sine squared is 1. You'd have to be very careful with your chain rule there, but I'm sure if you put your mind to it, you could do so. Was there a question? No? Okay. So our area, which is the double integral over d of 1 dA, if we turn it into a line integral along C, where C is the boundary of D, then the line integral becomes, let's have a look, equals, if we use that first one where Q is X and P is 0, we'd end up with X dy. But if we use that second one where P is minus y and Q is 0, then we'd end up with minus y dx. If we use that third one, the one with the halves in it, we'd end up with minus a half. Let's have a look. Let me write that slightly differently. Minus y dx plus, sorry, minus a half y, gosh, sorry, I'm being careless here. Minus a half y dx plus a half x dy. Remember, the thing that makes q q is it's the thing that's sitting next to the dy. And the thing that makes p p is the thing that is sitting next to the dx. Okay? And all of those are fine, and of course there are infinitely many options. And this one over here is the sort of popular one. It's the one that you'll run across conventionally. This is the one we see most often. But really, you could use any of those. Now, in going from the line integral to the double integral, you're given a p and you're given a q, and you have to work with those. Here you are not. You are choosing to recognize your double integral as Green's theorem being applicable in its context. But you don't have an explicitly defined p and q. And it's up to you to design them so that the integrand that you've got is the integrand that you would get given that the integrand is dq by dx minus dp by dy. Question? No? You fine? Okay. Okay, so let me demonstrate with exercise, whatever number it is, 35. And the little formulas that I've given there are in the box on page 66. So I will demonstrate with exercise. Ooh! That was fun. 35. There we are. Evaluate the area of the ellipse x squared over a squared plus y squared over b squared. Now this is at least the third time in this course that we're evaluating the area of an ellipse. I hope by now you know what the area of an ellipse is. Remember in linear transformations we did it? And we probably did it it will have popped up in the Jacobian section as well. What is the area of an ellipse? That ellipse.
That was plus something.
Yes. In this case it would be pi AB, because R1 and R2 are A and B. You have derived the area of an ellipse at least twice, well, I would say twice in this course already. And I can in fact find one of them quite easily. The other one I won't be able to find so easily. Where's linear transformations? Hello linear transformations, where are you? You're around here somewhere. Yeah, how about 75D, page 52, 75D, finding the area of an ellipse, but I'm pretty sure you did that in 69B as well. They're just slightly different flavors of the same problem. So there's twice, but basically using the same technique. But I'm pretty sure it pops up somewhere in the Jacobian section as well. That one I would struggle to find as easily, but I'm sure it's there somewhere. where you turn an ellipse into a circle with a coordinate change. So if you're looking at that and thinking, no, I don't remember ever working out area of an ellipse, either you didn't do those problems, or you're forgetting work that you've done. And what does that mean? I suppose it means you need to revise in all your copious free time. I know you've got lots of free time because you don't study any subjects except maths. Right? Wrong. Is that true? Okay. Evaluate the area of the ellipse using Green's theorem. So the area of the ellipse is integral dA, call ellipse D, 1 dA, call the boundary of D C, equals. All right. So now I want to turn it into a line integral, which is great. I can write down one of those formulas that I've just scrolled past. Well, I could write down that one that's at the top of the screen, or one of those ones that's in the box there on page 66. But of course, I'm now going to have to carry out that line integral, which means I need to parameterize my boundary curve. But that's easily done for an ellipse. It's going to be A cos t, B sine t, where t goes from 0 to 2 pi. Okay, that's parametrizing the boundary curve, parametrizing the ellipse. I'm saying call the ellipse D, it's really the region within the ellipse. Call region inside the ellipse D. The ellipse is the curve itself really, not the region within it. Okay, so I'm going to say area is equal to C minus a half y dx plus a half x dy, or you could use one of those other two, or you could make up one of your own. There are infinitely many options here, because there are infinitely many p's and q's that make dq by dx minus dp by dy equal to 1. So this is equal to, I'm going to turn everything into t, so this will be 0 to 2 pi, minus a half, y is b sine t, dx is going to be minus a sine t dt, but I'm going to push the dt right to the end, plus a half, x is a cos t, and the dy will be b cos t, and then here's my dt for the whole thing. Okay. And then I integrate that, sorry, there was a page jump there. Okay, so that's equal to 0 to 2 pi. Let's just tidy up a little bit. It'll be ab over 2 sine squared t plus ab over 2 cos squared t. Oh, that's rather nice. Because I can take the ab over 2 out as a common factor and pull it out of the integral, and then inside the integral I've simply got sine squared plus cos squared, so it becomes ab over 2 integral 0 to 2 pi dt, which will just be 2 pi. So this is 2 pi times ab over 2, which is pi ab. Okay, and I'll say what I have said before, which is a circle is simply a special case of an ellipse, where your a and b are actually equal, and we usually call them r for radius. And of course, in that special case, pi ab would be pi r squared, which is exactly what we would expect for the area of a circle. So the area of a circle is in fact simply the special case of area of an ellipse. Isn't that cool? Yes, it is cool. Question?
I don't understand what the equation minus half y dx plus half x dy actually is.
Okay, I'm going to scroll up. If you haven't copied, finished, then that's fine. I will come back. I'm scrolling back here. Okay, so I'm choosing to recognize this thing as dq by dx minus dp by dy. Why am I choosing to recognize it as that? Because if I do, then I have Green's theorem as an available tool. Okay, and so that thing in the brackets is equal to 1. So what is p and what is q? There are infinitely many options for p and q. One of them is one option is p equals minus a half y and q equals a half x, because if so, then dq by dx is a half and dp by dy is minus a half, and so I end up with a half plus a half, which is 1, okay? But of course, there are infinitely many options for p and q. The statement of Green's theorem says that the double integral of dq by dx minus dp by dy dA is equal to the line integral along the boundary of p dx plus q dy. So I'm choosing to take this minus a half y as my p and put it into that line integral, and the half x as my q and put it into the line integral, and then solve that line integral. Does that answer your question? And at the risk of boring you, I'll say again, there are infinitely many options for P and Q. This one, I think, simply because it spreads the load equally across P and Q, is the most popular one. Question?
Is there any particular way that we have to choose P and Q in relation to each other? Or can I literally just choose anything for P and anything for Q? They don't have to have any kind of relationship.
They don't have to have any kind of relationship. You can choose anything you want for P and Q as long as they fit that dq by dx minus dp by dy equals 1.
Okay.
That's the only constraint on P and Q. Yeah, so you really can choose anything, and yeah. So that's quite a nice one, because as I say, it spreads the load equally between P and Q, and they're linear. But you might say, well, I just want to go for the P equals, or rather the Q equals X and the P equals 0, because why not? Isn't that one easier? Question over there?
That was my question. Would
Yeah.
it be easier to do that?
Look, I think it probably would be. I'm just kind of reporting on what you'll find in the literature, what you'll find in textbooks. It's this half-half one that you'll see most of the time. And if you look in past tests and exams, sometimes you're actually told to use that one. Basically just to make marking easier, so we don't have 160 people all choosing different P's and Q's. Question over there?
So when you choose P and Q, do you just have to choose it so that the derivative of P with respect to Y and the derivative of Q with respect to Y, when you subtract them, gives you the original double integral?
Yes, so in fact you could apply this replacing double with line integral with any double integral, as long as you design your P and your Q such that dq by dx minus dp by dy gives you the integrand at hand in your double integral. Typically we see it in the context of areas, but it could be anywhere else. You had a question? David?
Yeah, I was
You're fine.
thinking, like,
Okay.
it seems like unnecessary complication. Why are we using the half x and half y?
My taste, in fact, goes for just using the Q, making P 0 and making Q x, because to me that seems like the easiest. Look in textbooks, it's not mostly what you'll see. I beg your pardon?
Could you do an example, one of the examples we're going to do in that style, so we can see how it can turn?
Well, shall we try and do this exact one? This exact problem just using one of the others. Let's do that. How about if we used Q equals X and P equals 0? Then we would have had our area, which is a double integral of 1 dA of d. It's going to be the line integral, let's have a look, of, well, just to be completely pedantic about it, it would be 0 dx plus x dy. So when I turn everything into t's, that'll be 0 to 2 pi. The x would be, what was it, a cos t. The dy would be, what was it? It was, y was b sine t, so when you differentiate it, it's b cos t. And there's a dt. Okay, cool, so I'm going to have a cos squared. So I'm going to have an AB, which I'll take out. Integral of cos squared, I'm going to have to use cos double angle formula. I know that cos of 2 theta is 2 cos squared theta minus 1. So cos squared theta is cos 2 theta plus 1 over 2. So that's the integral 0 to 2 pi. I'll bring the half out. Cos 2 theta plus 1 dt. Oh, sorry, not a theta, but a t. Okay. And that'll be AB over 2. It'll be a half sine 2t plus t from 0 to 2 pi. That'll give me 4 terms, of which 3 will be 0 and 1 will be 2 pi. And so once again, I'll get pi AB. Sine of 4 pi is 0, and sine of 0 is 0, and when I plug the 0 into t, I've got 0. So of those 4 terms I get, 3 are 0, only 1 is non-zero. So I suppose in this case, the calculation I've scrolled past was probably slightly easier because we didn't have to use a double angle formula. But in another context, maybe it wouldn't be. Really, yeah. But we did get the same result, which is comforting. It would have been extremely worrying if we hadn't. Everybody happy? Of course you're happy. You give it a go. Try number 36, which is basically the same. It's just I've given you numbers for A and B. But see if you can do it. Think, okay, what if I get this in the exam? How would I do it? Would I get it right? So you try 36, and the answer should be 12 pi. Okay. So Green's theorem we kind of do in 3 parts. There's the sort of straight up Green's theorem, which is the typical thing where we're turning line integrals into double integrals. Then there's going the other way, double integrals into line integrals, which we've just done. But then there is a special application of Green's theorem, which is to regions that have holes in them, which is not how Green's theorem is defined. If you look at the actual definition of Green's theorem, it requires what? A simple closed curve. And the region that's enclosed by the simple closed curve, in other words, a simply connected region, and regions with holes in them are not simply connected. So, Green's theorem for regions with holes, in other words, not simply connected. And even here, we're going to have 2 different kinds. We're going to have regions that come with holes in them, and regions where we actually make a hole. Okay. The basic statement of Green's theorem refers to a simple closed curve which forms the boundary of a simply connected region. It can be shown that Green's theorem can be extended to a finite union of simple closed curves and simply connected regions and can therefore be extended, and I'll give you some pictures to show what I mean, to what I'm calling regions with holes. In other words, regions which are not simply connected. Which are not simply, which are not simply connected. Okay, all right. And then the proof, I'm not going to give you a detailed sort of symbolic proof, but I'm going to draw pictures and give you some little formulas to show you what the basic idea behind the proof is. Okay, so let's say we have a region. I'm going to give it one flat edge. Here we go. And I have another region where I'm drawing them with a gap in between, but actually that's just for the sake of the picture. There actually isn't a gap. They share that boundary. Okay? So now those are 2 separate curves which are sharing a boundary. That gap is just for artistic purposes. They're sharing a piece of boundary, but each of those two regions is a simply connected region, and each of those individual curves can be recognized as a simple closed curve. This one goes around that way. Okay? We're assuming that, so this is in the situation where the boundaries are positively oriented. So on that piece of shared boundary, the one curve goes around in the one direction and the other curve's coming around in the other direction. Okay? So I'm going to call, let me put a dot there. In between those dots on this side, I'm going to call that curve C1. And I'm going to call this little shared bit C2. And then on the other one, I'm going to call this C3. And then I'm going to call the little shared bit, I could call it C4. But because it's the same as C2, just in the other direction, I can call it minus C2. Or I could call it C4 and then off at the side write C4 equals minus C2. So what we end up doing there is we end up saying that the double integral, let's call this D1 and let's call that D2. Double integral D1 of some integrand dx minus dp by dq dA plus the double integral over d2 dq by dx minus dp by dy dA. So same integrand but over two different regions. Now Green's theorem applies in each of those regions just by themselves. So we can say that, okay, just to save some space, let me come over here, is equal to, let's have a look, in D1, it will be the line integral C1 union C2 of P dx plus Q dy plus, and then that second double integral, the one that's over D2, is the integral along C3 union minus C2, P dx plus Q dy. Okay, now we know that if you work out the line integral along a union of curves, you can split it up. Sorry if I made a mistake.
dp over dx, the first one.
Ah, yeah, you're right. Thank you. I wrote a dp by dx where I should have written dp by dy. Thank you for keeping such a close eye on me. All right, so we know that if you're working out a line integral along a curve that is itself a union of different curves, that you can split it up. And this is the integral along C1 plus the integral along C2 plus the integral along C3 plus the integral along minus C2. Ooh, almost made it. I'm right at the bottom of a page, so if I press down, there's going to be a page jump. But it's fine, I'll just scroll back. Okay, and then, so that's four integrals. Integral 2 and integral 4 cancel. Because this one over here is just minus integral along C2 of P dx plus Q dy. Because if you flip the direction of a curve, that's fine. You can always flip the direction of a curve. You just put a minus in front of the integral. We do that in single variable calculus. Remember, the integral from a to b is the minus integral from b to a. You're always welcome to flip your direction in a line integral. You just put a minus in front, because it means instead of going one way, you just go in the other way. So whatever you were measuring in one direction, you're just measuring the negative of it coming back. So integral 2 and 4 actually cancel, and so we're left with just the integral of C1 plus the integral along C3. Which, if you go back to your original drawing, that just basically means the outer perimeter, the outer boundary of the union of those two blobs. We're basically saying that the shared boundary in between them doesn't matter. So basically, I can't remember what my blobs look like anymore. Basically, we're saying Green's theorem applies to the union of these regions. Okay? And as long as you keep those regions finitely many, because things always go a little bit screwy with infinite anything, as long as you keep the union of those regions finite, you can actually extend this. You can put a blob next to a blob next to a blob next to a blob that they're all touching, and you can say, okay, Green's theorem actually applies across the union of these blobs, these regions, these simply connected regions. And so, taking this to a rather interesting close, we can say, well, what if these blobs were basically horseshoe shaped? What if the regions looked like this? What if we had one region that looked like this, and the other region that looked like that? Well, we've just said that you can take those boundaries and you can rub them away, and you can say that Green's theorem applies to the union of these two regions. In other words, Green's theorem applies to regions with holes in them. Because that's what that'll be. That'll be a region that is connected, but not simply connected because it's got a hole in it. We can conclude that Green's theorem applies to regions with holes in them. Okay?
You have to describe that using curves, which use 4 curves for each horseshoe.
1, 2, yes, each of them would have to have 4, yeah. The 2 little straight bits and the 2 curvy bits. Yeah. Okay. Right. So then, what we're going to look at is we're going to look at 2 cases. We're going to look at, so we shall look, have I scrolled too far? We shall look at 2 cases. And those 2 cases are, they're going to, I'm phrasing them very colloquially. I mean, holes is not really a technical term, but you know what I mean. Holes already present. Holes we deliberately make. Why would we want to do that? We'd want to do that if we have a boundary curve where P and Q are very happily defined along the curve, everything is great, and then we want to do we want to use Green's theorem, and so of course then we're interested in the region that's inside the curve. But what if there's a point inside that region where P and Q are not defined? P and Q have to be defined everywhere inside the region, and in fact even a little bit outside the curve. That's what that open region containing D is all about in the definition of Green's theorem. So what we then do is we say, well, we desperately want to use Green's theorem. We desperately want to avoid doing the line integral and rather use the double integral. So what we're going to do is we're going to draw a little dotted line around the point that's the problem, and we're going to define a new region that's actually the region without that point. Or we're going to take a pair of scissors, we're going to cut away a little hole, and we're going to say, ta-da! Here's our region. P and Q are totally well defined on that region. The problem there is that that region that we've defined now has a boundary that isn't just the outer curve that we're really interested in, but it's also that little inside curve that we've just put there. And so we have to then deal with the consequences of that. So we're pretty much at the end of the period. So what I'll do here is I'll just kind of give you some numbers. The hole's already present. You've actually encountered one of those already, or you will in the tutorial. Exercise 33 is like that, and so is 39. And then the ones with holes that we're going to make are 40, 41, and 42. Okay, I'll stop there, and then tomorrow we'll start with that, and then we'll also have to start on Stokes' theorem before the end of the day, because we were a lecture behind, we're now a lecture and a half behind our own schedule. And I've built in one buffer lecture, but I haven't built in two. So tomorrow we'll do some exercises on this. We'll do 39 and 40, and we'll start Stokes' theorem.